Sounds Jatra, and a good day. Sample size considerations in animal experiments are an integral part of any successful research. So let's look at what will be the factors that determine sample size considerations. Well, I guess everybody will have remembered this type of approach. Back in the 80s, 90s, well, people were actually looking for significance. And how do they hunt for significance? They practically go for how many stars that you can see upon uh, concluding statistical testing in all of your experiments. The more number of the stars, the better the results. And therefore, we come to the conclusion, for example, there will be significant, highly significant, extremely significant, and so on and so forth. But we do know that deep down, this is actually not right. And therefore, you may not see this kind of expression anymore in most scientific publications today. We just simply see that there will just be statistically significant or non-significant. That's all. Why is that so? There is the one reason is that there are flaws to the statistical methods that we are using today. Significance actually can be influenced. The level of significance can actually be influenced by the sample size. The more sample size that you use, the so-called more significant or highly significant is going to be. So in this case, it makes no sense for us anymore to look at just highly significant or significant. What we need now is actually some results that we can trust, some results that will not change when the sample size changes. Let's move on further to talk about the dilemma between choosing a big sample size and a small sample size. Of course, people always say that big sample size is good, but big sample size will complicate things because then you will have more samples to handle, the cost could be even prohibitive. Cost in terms of time and money. For example, if let's say one procedure will take you half an hour to perform on one animal, and you have 40 animals, that would have meant that you need to work 20 hours continuously to sample the first until the last animals. So you have to ask yourself, is that possible? It may not be possible. So then you may be forced to spread your work into what, 3 days, 4 days. And if you spread your work across 3 or 4 days, then you have to ask yourself again, are the results from the first animal going to be the same as the result in the last animal after within that course of 4 days? You do know that biological organisms undergo diurnal rhythm, and to some extent, some of their parameters changes according to the time of the day. So this is actually something that we need to pay attention to as well. Then again, there are ethics and welfare requirements that we may need to adhere to. We cannot use more than the number of animals that has been approved. And in experiments that involve death to animals, we cannot use a big sample size because that will be violating the ethics on welfare consideration. So how do we choose a sample size? Of course, we can only use statistical and scientific approaches. And of course, there are specific requirements under specific testing that will require very, very minimal number of animals. For example, toxicology testing as per OECD guidelines, which will require us to see certain appearance of certain adverse signs. Obviously, you cannot do that on a big pool of animals. Well, this could be the scenarios that we are viewing, we could be encountering. For example, well, the first scenario, too many animals. You can see here an animal science project requested for 500-day-old chicks to assess effects of feeding 5 levels of probiotics on growth, meat quality, and carcass composition. So in this case, points to consider may include necessity or justification of treatment levels used. Why do you need 5 levels? Distance or difference between levels used. The distance should be sufficiently different so that it will not be influenced by your mixing or administration techniques. If let's say you're only capable of administering a technique with a minimum difference of 100 milligram between 2 treatments, so it makes no sense for you to assign treatment that uses 1 or 2 milligram of substance. Feasibility of handling this many animals? Well, in animal science project, this is something that is very common. But, well, is it the same that you want to do for your experiments? And when you have so many animals, time taken, the procedure, the cost, and so on and so forth will become rather prohibitive. And most important of all, is that an accepted practice in that field of expertise? Talking about which we're going to switch to the next one. This is another extreme whereby there are too few animals to be used. In a theriogenology experiment, this is typically accepted. They use very minimal number of animals because they are using prize animals. Prize animals are extremely expensive animals. They could be costing thousands, tens of thousands, or even hundreds of thousands or millions in terms of dollars and ringgits. So of course, it makes no sense for you to say that I want 10 animals or I want the animals according to my sample size calculation. So heterogeneity animals that utilizes prize animals will be realistic when there are considerations taken into what that particular field is trying to achieve. So in this particular area, they typically will be able to accept few animals, but they will require much more higher repeated samplings for that same animals to account for variation. Then there will be issues about pseudo replication, and of course sample size calculations will have to be made based on mixed model or some kind of a repeated measure model. Then we move on to the middle ground. This is an experiment that maybe most of us will have understand. A biomedical research requested 40 animals in 4 equal groups of 10 animals each to assess 2 active ingredients and 2 control groups under evaluation. Points to consider at this stage may consider, is it necessary for the control groups to have the sample size? Well, yes and no. Very much depends on how much signal to noise ratio. Signals in this case tells us effects, whereas noise indicates experimental error. And of course, what is the N for the control group justify in terms of the modes of action and other grounds of comparison being considered? Preferably, the control that you choose should mimic the expected mechanisms that you see in the animal experimentation. And sometimes we may need to include more animals in the control group to improve overall sensitivity of comparison. Read the article by Bate and Karp, 2014, published in PLOS ONE, available through this particular link here. And that brings us to the next debatable debate. What is so great about statistics? Well, I can tell you there's none at all. Statistics never prove anything. They only indicate likelihood or results of investigation being the product of chance. It can only be a very powerful summary tool, linking all related variables and factors in the research to be considered together, provided all experimental and statistical assumptions are correct. If the assumptions are incorrect, then there's nothing proud to be talked about statistics. The N is critical because it determines the validity of the trial. Well, it also the way that you economize the research or time and labor costs involved to carry out the research. In real life, we are restricted in terms of sample size, in terms of our resources available, and the cost per sampling unit. But then I like to caution everybody again, this particular formula that I depict here is not a formula to calculate sample size. I repeat, the formula depicted here is not the correct formula to calculate sample size. I'm just merely illustrating the fact that we are constrained in terms of resources when we carry out experimental work. And to complicate matters further, publications often do not tell you the success rates of the procedure. So therefore, if let's say they say that they are producing animals from a certain disease condition, well, the actual numbers used could be even higher because the success rates to produce certain animals from certain diseases may be much. Maybe something that you need to ask the authors all about. For example, you look at this: the induction of diabetes in STZs using streptozotocin. At 40 milligram per kilogram, mortality rate can be 20 to 30%. Success rate is about 75%. That means of 4 animals induced, only 3 are going to show the diabetic change, but the effects may last only 6 weeks. And then factor in mortality, you can see that if let's say the research reports using 100 animals, you can easily assume that it is not 100 animals that they use as starting animals. They could be using more than 100 animals in this case. And then at certain dosages, mortality rate can be much higher, and success rates, even though it's higher, well, and even longer effects, but animal may get corneal opacity. Well, you may say that corneal opacity is something that is common to diabetes, but in this case, you may also need to be mindful that this is actually an after poisoning effects caused by streptozotocin. So in this case, it becomes important for us to know how to calculate a starting sample size. The third point that we need to consider is that the SUC forms, or animal care and use committee forms, often ask about what is the justification for the number of animals requested. Justification must include the three of the following: a clear description of experiment design, which are not methods or procedures, specification of the numbers and species and strains of experimental or control animals per group or subgroup in each experiment or procedure, and then the scientific or statistical rationale which supports the size of n in each of the group. So this is actually something that we need to know. So our subsequent sections will actually attempt to help us understand and recommend the best choice of sample size. So let's look briefly at sample size. Sample size very much depends on types of control used, whether you use animals as your own control or whether you created a special baseline groups of animals to do the baseline study, and whether you are having parallel controls. So if you're having both baseline and parallel controls, obviously you could be adding the number of animals. And then types of experiments used. Whether you are looking at pilot or formal testing hypothesis, if it is a pilot trial, of course, you use much less number of animals. And structure experiment design, how you structure the groups and replications. The more factors that you introduce, the more groups that you need to incorporate. For example, if you let's say perform experiments to determine whether two dosages are effective against an animal, and later found out that the dosages are differed in terms of effect across a gender. So that means you have to check those two dosages in the male and two dosages in the female. You can see that by introducing the gender factor, you effectively double the number of animals required. And then of course, the magnitude of observed effects. How remarkable or how strong are the effects are, and how observable the effects are. So this one is known as magnitude of observed effects, which we'll talk about later. And of course, precision of measurements, how repeatable the methods are being in terms of showing the results again and again. Statistical methods employed also determine the sample size, as do the significance. If you are going for higher level of significance, for example, 99% significance, then of course, you need more animals to prove it. The next concept that I want to introduce to everybody will be the power of the test. Power of the test is the ability or chance of correctly detecting a true treatment effect when the test itself is significant. Try not to confuse this with significance. Significance means confidence, how confident you are with the results, whereas power of the test actually tells you how the chance of correctly detecting a true treatment effect when the treatment is there. Typically is set at 70 to 90% and above. And of course, finally, sample size is also dictated by internationally agreed guides or standards or conventions in generally accepted methodologies, which differ according to the field expertise, as per the three examples I already indicated at the start of this slide series. Types of controls I've already mentioned to you just now, depending on how many groups that you introduce as control, then your number of animals will of course have varied. If let's say you decided to include a baseline control whereby the animals are tested prior to the start of experiments, then of course you have that additional groups of animals and number of animals to take into account. And of course, this one very much depends also on the techniques that we use. OECD guidelines for toxicology testing typically will have additional requirements for selected groups. The next one, as I mentioned earlier, will be the pilot trial or actual animal procedure. This is important because, well, sometimes for certain experiments that you may not know work or will not work, the ICOC committee, IICUC committee may want you to perform a pilot trial to prove it. And as a result, you may need to calculate the success or failure rates as indicated earlier. So the success or failure rates can be calculated using this formula by Dell 2002. And this formula takes into account the power of the test. Okay, power of the test. And as you can see, depicted by the formula here, N is actually the ratio of log beta over log P prime, where beta is actually the chosen power of the test. So you can see earlier, power is actually the ability to detect an effect when the effect is actually there. And the P prime is the proportion of animals that did not have the desired goal. So you can see here, this is actually a ratio telling us, well, what is the chance of correctly detecting an effect versus the proportion among the animals that do not show the desired desired effects. So this in itself is actually a very powerful summary of how many animals that you need to use for your trial. And the following slides showed you the sample calculations using this Adele formula. So you can see here, assuming success rates producing transgenic animals is 5% and investigator only have about 90% chance of getting the transgenic, then you can see here that this calculation worked out to be that you need about 45 animals to produce one animal. So obviously, if the article says that they only use 10 animals, based on these calculations, you will know that they are not using 10 animals. These 10 animals could be derived from 10 times 45 animals, which means 450 animals. At this stage, you also have to ask yourself, can you do this type of trial? Can you replicate this type of trial using whatever resources that you have? So please read further beyond this method description of each of the article that you are going to see. And the same formula can also be used to prove whether an animal colony is free from diseases or otherwise, as you can see here. And of course, experiments designed for formal testing hypotheses usually require more elaborate knowledge of sampling population, variables measured, experimental design employed, effect size, test power, confidence, and estimates of variability of precision. And these are the point where we can be incorporated into specific formulas of those Cochrane and Statistical, Altman's nomogram, statistical softwares to estimate sample size. Now, let's look at a few other approaches. Before that, I'd like to introduce you to G-Power3, which is actually a free software that you can use to calculate sample size. It is downloadable from Universität of Düsseldorf, whereby if you use them, you can actually quote their references as indicated here on the slides. These two references, published in Behavioral Research Methods, 2007 and 2009. Sample size determination is something that is very important, as I already implied to everybody at the beginning of this series of slides. In order to calculate sample size, we need to know the effect size. Effect size is actually the magnitude of effect. If the magnitude of treatment effect is very, very obvious, then obviously the sample size will be much reduced. But if the effect size is minuscule, then you need more animals to actually demonstrate that. And in general, effect size can be measured in two ways, as a standardized difference between two means or as a correlation between independent variable classification. And this correlation is called the effect size correlation. Now, let's look at an example. Why do we need effect size? Because any given experiment can be statistically significant if given large enough sample size. And this is actually the flaw that I already depicted at the second slide. Of this slide series. Remember the highly significant, and extremely highly significant examples I've given you? Well, that is only because we use bigger sample size. So if you use bigger sample size, any given experiment can be statistically significant. So this is actually something that is very scary. Why? Because there are flaws with the analytical technique that we use. I will just use the one-way ANOVA as an example because one-way ANOVA has been used throughout the ages as the de facto testing method for all kinds of experimental results comparisons. ANOVA is actually based upon the premise of trying to detect treatment effect across treatment groups, differences across treatment groups in terms of treatment effects. And of course, since we are dealing with biological organisms, each of these organisms are different from each other. And since they are different, they are considered to be having some degree of error. So when they are having some degree of error, this will further complicate the outcome of the results, outcome of the experiment, sorry. So in this sense, whatever treatment effects we have already gathered need to be contrasted against experimental error or corrected against experimental error. So this gives rise to the ANOVA. As you can see here, ANOVA has two components. It has treatment effect, which is between groups, divided over experimental error. Naturally, you want the treatment effect to be as big as possible and experimental error to be as small as possible. Then again, you also have an impact of getting more animals into the trial. So more animals into the trial will actually allow us to see the treatment effect or the experimental error better. So in order to account for that, one-way ANOVA came out of this formula. I can tell you that the formula is being arranged in a similar way for two-way ANOVA, repeated measure ANOVA, and many others. The only thing is that the other considerations that they include will be very, very different. So in this case, you can see, assuming that you have a very strange experiment whereby treatment effect is the same experimental error. Okay, I repeat, treatment effect is the same as experimental error. So that means the treatment effect is as large as the experimental error. Obviously, this is not a very good experiment. Then this part of the ANOVA equation will become 1. And remember, this equation is important because it will determine the so-called F value. F value is what tells us whether an ANOVA is significant or non-significant. So when it is actually more than 3, 3.8, and so on and so forth, then your ANOVA analysis will become significant and your overall statistical test will become significant. So in this case, you can see here, when you have a treatment effect that is the same experimental error, then the F value or significance of ANOVA will be determined by the total sample size only. In this case, you can see here. So we do not want sample size to determine our significance because they are amounting to cheating ourselves. Because it becomes even more important for us to actually see whether our treatment is actually having any effects or not. Can you imagine this? What happened if, let's say, there are 63 subjects in 3 groups? Okay, so as I've already mentioned to you just now, let's say this one is actually treatment effect the same as experimental error. So this X section of the value will be 1. And then 63 minus 3 will be 60. Number of groups will be 3 minus 1 will be 2. So that means 60 divided by 2 will be 30. So in that case, okay, if that's the case, if you have F value of 30, I can guarantee you that the ANOVA will be very, very, very significant. Okay, but then again, we have to revisit the fact that this is actually from an experiment whereby treatment effect and experimental error is actually the same. So obviously, we are cheating ourselves. So in order to combat this, then we have to go for the effect size. Effect size is actually based on the concept that you just need the optimal number of sample size in order to attain the significance that you wish to see in animals or in the animal experiments. As you can see here, this is an experiment to examine effects of drug A on liver metabolite in rats. Group A has 8 subjects treated with drug A, and group control also has 8 subjects treated with control. So in this case, you can see here that the effect size is actually 1.1. To estimate the effect size, how do you do it? You just fit all these figures into the formula that I already depicted earlier. Now, remember, this formula is actually only for a two-group comparison. For a three-group comparison, ANOVA, repeated measure ANOVA, and many other methods, you may need to refer to the formula itself and get a much more accurate estimation for each of the models that you are employing, something that you need to be mindful. Then again, having said ES, we already knew that we calculated our ES will be 1.1. So what is the, well, appropriate ES then? ES is actually something that will actually allow us to project whether it's worthwhile doing an experiment or otherwise. If we have an ES of 0, it means that there's no possible difference between treatment and untreated group. So we are wasting our time with animal experiments. Conversely, if the ES is more than 4, it's considered perfect. So that means you need less than one animal in any experiment to prove that there's treatment effect. In other words, no experiments is also necessary again, unless you want to show that you can obviously get an impact from this kind of trial. Large ES is typically denoted as ES that is actually anything more than 0.6, whereas medium ES is actually anything from 0.2 to 0.5. But obviously, we could typically see ES in the range of about 0.2 to 0.5, or maybe just around 0.6. So how do you use the next tool in this case to determine sample size? Let me introduce you to the Altman's nomogram. Altman's nomogram is actually, as per what is being depicted here, is actually found in the book indicated here on the lower right, Altman DG, 1991, Practical Statistics for Medical Statistics. You can easily retrieve this type of graph from just by Googling for Altman's nomogram on Google, and you can actually use it immediately. Remember, we are trying to calculate sample size from prior research using effect size and based on whatever that you have seen on Altman's nomogram. Recall that we have these particular experiments whereby we already calculated that the ES is 1.1. We know that there are actually 8 animals per group using this subject, but we need to know whether, based on these kind of changes, number one, whether it is appropriate, and number two, whether 8 is actually something that we want to follow as well in our own experiment. So based on this, you can actually try to fit all the values in. We knew that we already got an ES value of 1.1, so we plotted 1.1 here. And then we plotted another point of reference at the power axis. Power is the ability of the test to detect a significant effect when detect an effect when the results are significant. So in this case, you can see we put as average as 0.8. So by connecting the dots between 1.1 effect size here and 0.8 here, you can see that it crosses the significance, the line. So the significance here, one of it denotes 95% significance level, the other one 99 significance confidence confidence level. So 95 confidence level, 99% confidence level. So in this case, you can see at 95 confidence level, the line crosses at 26, around 26. Now, bear in mind, the numbers depicted here are sample size, total sample size depicted by this capital N, not small n, capital N. So this is total sample size. So in this sense, what you can see is that total sample size is 26, and since we're calculating for 2 groups, so each group will be 13 animals. Now, if you are testing at 99%, do look at this point here. So it crosses at this region. So what you need to do is that you just move up according to this vertical line. As you can see that it is actually 40. So at 99% confidence level, you need 40 animals. And since this actually animal experiment involving 2 groups, so each group will be 20 animals each. So it's as straightforward as that by using Altman's nomogram. Alternatively, you can also use the G-Power software, assuming that we have ES of 1.1, and then all you have to do is just download a software and fit everything in and generate this particular graph, or you can even use just a numerical interface if you wish. So you can see here, the same results are depicted. 0.8 will be the test power, and then this is the curve built for this particular assumption, as you can see here. And of course, the sample size will be around 28 as well in this case. So, or 14 per group. Now, of course, obviously, we are using a method of estimation. So there will be some deviation in terms of sample size. But I do recommend that you use G power for much more accurate computation of sample size. As you can see here, it's more or less similar to what's been reported by outcomes nomogram. The third method is some method that not many people are used to, but it's been given in the book by Statistical and Cochrane, and they are using a formula. Suffice to say that once you have done everything, it also gives you the same results as what depicted in outcomes nomogram and in G star power. The next factor that determines sample size will be precision of measurements. In essence, precision means how repeatable one reading is. So the more precise the reading is, then the less animals you're going to use. If let's say the readings are not consistent, then, well, you're going to need more animals. More precision, higher precision also indicates that the experimental effects of interest is actually much more easily observable. Okay, much more easily observable. So what is the relationship between sample size and precision? As you can see here, there are two levels of precision here. One of them with a measurement of precision of 0.1. As you can see here, group 1, 91.5. At precision of 1.0, the group 1 reading becomes 92, and group 2 readings at 0.1 precision is 97.4, group 2 reading is around 97. So the difference between the two will be 5.9 in 0.1 precision and 1.5 for 1.0 precision. As you can see, based on the ES calculated, based on the sample size per group, is very, very different. So there's a difference of about 9 animals here. So please, the moral story here tells you that you technically need to invest in much more precise equipment to get better results. The other factor that we also need to factor in will be the design, experiment design. Experiment design is something that is very important because it will tell us how the treatments are being arranged, okay? And it will also affect the efficiency of the research methods in detecting treatment effects. The completely randomized design, which I already depicted here in the earlier slide using my rats as example, is the most basic form of experiment design, whereby you only have one factor and equivalent numbers across all groups. So this is a CRD. And sometimes, in order to introduce more factors, this type of design may not be applicable. You may want to replicate that. Okay, so you may want to, instead of CRD, you may want to use a different kind of experiment design known as the randomized complete block design. Randomized complete block design is investigating an effect of one factor while ruling out the effects of the other factor. And the data metrics typically follow two-way ANOVA. Okay, follow a two-way ANOVA. So this is a simple CRD design as what I've already depicted to you just now. And this is the RCPD design. So you can see here is a replicate of the CRD designs. But in this case, you introduce two factors. One will be a treatment factor indicated by group 1, 2, 3 here. The other one will be the gender factor indicated by the male and female here. So you can see the more factors they introduce, the more animals they're going to use. So what will be our decision on a complex design or a simpler design? We shall see in the next few slides. Then, of course, the RCPD is actually a subvariant of the factorial design. And you can also have a much more controversial or even a simpler design known as a Latin square, when you do not have enough number of animals to be rotated around and so on and so forth. So that, of course, I'll reserve it for the other topics. And not within the scope of the current work. For me, I can just simply tell you that try as much as possible to use a balanced design, namely a factorial design or RCPD rather than Latin square, because Latin square will introduce many other factors of unknown to the entire study design. So what makes the decision for us to choose either a much more complete RCPD or maybe a much more simpler CRD? We use an index known as design effect factor. This DEF serves to compare the efficiency of selected experimental design against CRD. So how do we do that? We calculate the pool variance of data using selected experimental design, maybe your Latin square, maybe your RCBD, and always compare it against the CRD. The CRD because it's the simplest experimental design. So if the DEF is less than 1, then new experimental design is better compared to CRD. If the DEF is equivalent to 1, then the new experimental design is comparable to CRD, so you still use CRD. But if the DEF is more than 1, new experimental design is not as good as CRD. Okay, so something that you need to consider and then to use the CRD. But if your DEF is less than 1, obviously here you can see that you should not use CRD. Instead, you should go for a much more complicated design involving more animals and so. For example, you suspect that your pilot data for a study attempting to compare effects of compound X on blood pressure in rats is showing noticeable gender effects. You proceed to compare the efficiency of CRD model versus RCBD model where you block the subjects by sex. The CRD design, you have 10 animals. RCBD, you have 2 groups of animals. But bear in mind that these are same readings. Okay, these are readings from the same animals, but organized according to gender, as indicated to you now. So you see all the numbers in the CRD design and RCBD designs are identical. Only that in the RCBD design, they are organized in males and females. Now, let's see how efficient the numbers are. In CRD design, the variance is 52. In RCBD, based on the variance calculation methods, pool variance calculation methods, you got 47.26. So the DEF in this case becomes 47.26 divided by 52 with a ratio of 0.91. So what does that mean? It simply means that the RCB design is actually much better. Okay, RCB design is actually much better. We know that's the case because we know that drugs had noticeable effects across differential effects across a gender. This is something that is well known. So I'm just using the example to illustrate these facts to everyone. The few other considerations about the sample size will, of course, involve the type of statistical test used. If you are running a parametric test on parametric data, which is actually something that follows normal distribution, and then you need to follow whatever depiction of the sample size calculation that we're already showing you in this series of slides. However, if you are doing experiments involving non-parametric data, which doesn't follow any type of distribution, which are not normal, as in layman's term, then the depiction of sample size calculation in this series of slides may not be applicable. Non-parametric data have their own sample size rules and conventions, and typically it's much more lesser as compared to the parametric data. And how do you differentiate between parametric and non-parametric data? You have to perform a test known as Shapiro-Wilks or a Kolmogorov-Smirnov test to show whether they are normally distributed or otherwise. Examples of these statistical tests are as depicted on this series of slides. If you are comparing a mean between 2 groups, then you can use the independent t-test. Whereas in the non-parametric form is known as the Mann-Whitney U-test. If you are comparing a PAT comparison, then you have PAT t-test, whereas the equivalent in non-parametric test will be Wilcoxon sign rank. The same likewise will be comparing for more than 2 groups, ANOVA, the equivalent for the non-parametric will be Kruskal-Wallis Hess test, and so on and so forth. And of course, other methods to transform data and perform two-way ANOVA as indicated on this particular sets of slides. Further descriptions for correlations, regressions, and others are as depicted on this particular slide. Well, having mentioned all those, what will be the conclusion? One thing that is sure, there are no absolute and foolproof approach for sample size estimation. The available statistical tools merely advises on the best option or the estimates available. And it's of course very important to refer to prior works and follow conventionally accepted sample size and methodology. This one will have the added advantage to help you when you need to defend your paper in light of the criticism or comments by reviewers. Because reviewers may not really trust your calculations, but they would prefer to look at what are the typical approaches in the published area. from a leading, of course, from a leading journal or from a flagship journal. And of course, finally, always remember, justification for sample size should scientifically and statistically sound while following the 3R approach, which is actually refine, reduce, and replace. I hope that after this, going through this series of slides, everybody should have the notion that we should use statistics for illumination rather than support. So before we go, I leave you with these cartoons over here, something that I'm cautioning myself and everybody else not to do when you're looking at statistics. We do not use it for support, okay? We use it for illumination, meaning that for us to understand the dynamics of research and why research turns out so, and using data to help us to make the best scientific decision. So I think with that, I thank you for your attention and have a good day.